So let's start with the following. So find the antiderivative of each function. The first one, the function, I'll give it a name. Oh, there's something in the chat. Let's see what's in the chat here. So way to find that page online. You know, I didn't post it. Actually, you know what? You can find it online. No, I kind of modified it though. The problem is the quality of it is not great. So I can email it to you, Evan, if you want. But yeah, I don't have it online currently. But hopefully you can read my writing and it's not too terrible. And we're gonna go through it all right now, so you don't really need to grab it later. So the first one is find the antiderivative of f of x equal to x cubed plus the fifth root of x to the fourth plus secant squared of x plus 7. So typically, it is often in your interest to rewrite things in a way that makes it easier to find their antiderivative. Whenever I have x to a power, I'm always going to rewrite it so it's actually x to a power. Right? The fifth root of x to the fourth, I would much rather write that as x to the 4/5 power. Right? It's x to the 4 to the 1/5, and then we multiply the powers and get x to the 4/5. Nothing to be done about secant squared or 7. That's fine. If I was using typical notation to write the antiderivative, I would probably write it as capital F of x. That's a pretty standard choice to use the capital letter version of the function name. Until we start using the antiderivative notation, which is just the integral symbol. We're going to be using the reverse power rule here. So we're just going to add 1 to the power, divide by the new power. So the antiderivative of x to the third is x to the fourth divided by 4. Which is fine. This one here is a little bit less easy. The antiderivative of x to the 4/5. If you don't know what 4/5 plus 1 is off the bat, just write 4/5 plus 1. That'll get you some credit. So the antiderivative of x to the 4/5 is x to the 4/5 plus 1 divided by 4/5 plus 1. Okay, here's where you have to know something. You have to know what function you take the derivative of to get secant squared. Which function is it? Tangent of x. And then constants always seem to be challenging. The antiderivative of constant, though, is super straightforward. You're looking for a function whose derivative is always 7. In other words, you're looking for a function whose slope is always 7. Can you think of a line whose equation has a slope that's always 7? I'm sure you all can. I'm going to say 7x. You could say 7x plus 5, or 7x plus 2, or 7x plus anything. But we don't. We just say 7x. And then, of course, at the very end, we slap on a plus c. Because you could literally add any constant you wanted, and it wouldn't change what the derivative would be. Now, I will say we shouldn't leave this like this. 4/5 plus 1 is 4/5 plus 5/5, which is 9/5. So I should really rewrite this as, you can leave this as x to the 4th over 4, or you can write it as 1/4 times x to the 4th. This will be x to the 9/5. Dividing by 9/5 is the same as multiplying by the reciprocal 5/9. So 5/9 times x to the 9/5. And then we have plus tangent of x plus 7x plus c. So just as a reminder, even though I know we talked about it a while ago because then we did like midterm review, but I think he's probably talked about it in class. The antiderivative of x to a power, written using the integral notation here, is x to that power plus 1 divided by that new power plus 1 plus a constant. And this is true as long as the power is not equal to -1. I usually call this the anti-power rule or the reverse power rule. Some people just call it the power rule, or the power rule for antiderivatives, but I think anti-power rule sounds more fun to say. Let's look at some more examples on this handout. So the next one is our function, let's call it little g of x, is 1 over x squared plus 3 over x plus 4 over 1 plus x. And this kind of brings up, I don't know, maybe an interesting conundrum in that most of the time I want to write something as x to a power. I mean, I don't want to write it as 1 over x squared. I actually want to rewrite this as x to the negative 2. And I'm actually I would encourage you not to copy down what I'm about to write because I'm going to change it anyway. You could rewrite this as 3 times x to the negative first. And you could rewrite this as 4 times 1 plus x parentheses to the negative first. But honestly, the negative 1 power is the only power I really don't like writing as a power because I know I'm not going to be able to use the power rule. I can't add 1 and get 0 and then divide by 0. Divided by 0 is not a big deal. It's not good at all. So instead of doing this, I would probably actually leave it as x to the negative second plus 3 times 1 over x, or if you prefer 3 over x, although I kind of like to see the constant out in front, plus 4 times 1 over 1 plus x. And then to find the antiderivative capital G, here I am going to use the anti-power rule. I'm going to get x to the negative 2 plus 1 divided by negative 2 plus 1. Here, let's talk about constant multiples. Constant multiples, just like with derivatives, with antiderivatives also hang out. The derivative of 3x to the fourth is 3 times 4x cubed. The antiderivative of 3 times x to the something is going to be 3 times the antiderivative of that something. So I always like to say constant multiples hang out. Constants on their own do a different thing, right? The derivative of a constant is 0. The antiderivative of a constant is that constant times whatever your variable happens to be, usually x, just like we had the 7x in the previous problem. Here, the 3 is going to hang out, and the antiderivative of 1 over x, I know we also did talk about this, but I know it's also been a while, is the natural log of the absolute value of x. Yes, you do need the absolute value there. Eventually, I'll point out a time when occasionally sometimes people drop it with good reason. You should always err on the side of caution and just write it in there. Now, this one actually kind of is getting at something we're going to talk about a little later, but I'll just say the 4 is going to hang out, and the antiderivative of 1 over 1 plus x is the natural log of the absolute value of 1 plus x. Ignoring the absolute values for a second, the derivative of the natural log of x is 1 over x. The derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff. So if you check here really quickly, the derivative of the natural log of 1 plus x is 1 over your stuff. And then what do I multiply by when I use the chain rule? What's the derivative of my stuff in this problem? I know you know. You can say it. It's not like no one's going to judge you. What's the derivative of this stuff down here? Just 1. That's what, but what I want you to is like, sometimes if your stuff down there is a little bit more complicated, natural log is still the way to go. And we'll see more of this as we move on. Oh, and then what did I forget? Plus C. Gotta have the plus C. And then we should simplify this a tiny bit. I would write this as x to the negative 1. Or, oh, actually, I really wouldn't. I really wouldn't write it as x to the negative 1 over negative 1. I would really write it as negative 1 over x, because that's how I prefer to write it. Plus 3 natural log of the absolute value of x, plus 4 natural log of the absolute value of 1 plus x, plus c. There's your antiderivative of that original function. Yeah, we should do one like that too. We'll get there. Okay. As always, if you have questions, you should ask them. Can I organize my papers? Maybe. Let's look at the next one on this handout. Got 3 here. Let's call it lowercase h of x is equal to cosine of x plus 1 over the square root of x. I don't know what the antiderivative of 1 over the square root of x is without rewriting it first. So we should rewrite this. I want you all to rewrite this as cosine of x plus x to the appropriate power. I'll give you 20 seconds. I wasn't keeping track. I think that's been about 20 seconds. The power here should be x to the negative 1/2 power. It's positive 1/2 in the denominator, then you bring it up, it becomes the negative of what it was. And now anti-differentiating. Okay. I don't want the derivative of cosine, which is negative sine. I want the function that if I take its derivative, I would get cosine, which is positive sine. The derivative of sine of x is cosine of x. So the antiderivative of cosine of x is sine of x. Plus, just going to use the anti-power rule here. It's going to be x to the negative 1/2 plus 1 divided by negative 1/2 plus 1. You don't need to write all that out. If you can do that work in your head, I think you should. But it's also good to see what we're actually doing, so you remember what we're doing. Let's see. So negative 1/2 plus 1 is negative 1/2 plus 2/2, which is positive 1/2. And then dividing by 1/2 is the same as multiplying by the reciprocal, which is 2. So I'm actually going to rewrite this as sine of x plus 2 times x to the 1/2 plus, excuse me, plus c. I would honestly probably actually write it as sine of x plus 2 times the square root of x plus c, but it doesn't really matter, right? The same thing. I just have a preference for one versus the other. You know why I have a preference for one versus the other? Honestly, the reason I would maybe write it as sine of x plus 2 times the square root of x plus c is that for me, if I write it this way, it's easier for me to see that this derivative has some domain restrictions. Right, x can't be negative here. Whereas for whatever reason here, it's just not as obvious to me that x is in the square root and I don't get negative. There, it just looks more, I don't know, stuck. But that's why. Okay. Moving along. Let's look at the fourth one on the sheet. So now we are using this integral or antiderivative notation. Again, so when I write indefinite integral, that's just another way of saying antiderivative. As far as any of us are concerned, they literally mean the same thing. So if I want to find the indefinite integral of x to the 5th times x to the 4th plus 1 squared dx, we're just going to multiply it out. We don't really have any other choices here. And that's usually a good tactic, right? If you see something that you can deal with by just using some algebra, it's often the right way to go. So I've got my x to the 5th here, and x to the 4th plus 1 squared is going to be x to the 4th squared, which is x to the 8th, plus 2 times x to the 4th times 1 plus 1. I'm just using the a plus b squared is a squared plus 2ab plus b squared. And then distributing the x to the 5th to each of those three terms, that's going to be the indefinite integral of x to the 5th times x to the 8th is x to the 13th. X to the 5th times 2x to the 4th is 2x to the 9th. And x to the 5th times 1 is just x to the 5th. So what I'm trying to exemplify in these problems is that if you can write something out as just powers of x, that is often the right way to go, because then we can just apply the anti-power rule to each of those pieces. So here we're going to get x to the 14th divided by 14 plus 2x to the 10th divided by 10 plus x to the 6th divided by 6 plus c. And I would probably simplify the 2x to the 10th over 10 as x to the 10th over 5, but I don't think we need to waste the ink at this moment in time. So there's your antiderivative or your indefinite integral. I do want to point out that this symbol here, that curly look, that elongated S, which I think is actually what it is. It's an elongated S to mean like the sum of all these things. So we're actually looking at something that's supposed to be a sum. And this dx here, those are just instructions. Those are instructions that tell us to anti-differentiate. The dx part just tells us what variable we are anti-differentiating with respect to. In this case, with respect to, that's what that abbreviation means, WRT, with respect to the variable x. And notice that in each of these steps, I kept writing that symbol until the step where I actually did what the symbol told me to do. Just like if you were to see me take a derivative of something, like say the derivative of 1 over x cubed plus 1 over, sure, sine of x. Before I took the derivative, I would rewrite it, still writing the instruction that tells me what to do, because I haven't done what the instruction told me what to do yet, of x to the negative third plus cosecant of x. And then I would actually do what the instructions tell me to do. So I no longer write the instructions, and I get negative 3x to the negative fourth minus cosecant of x times cotangent of x. So keep writing the instructions, just like we keep writing a limit or a derivative or an integral symbol until you've actually done what the symbol wants you to do. Okay. Sure, I can move papers out of my way, maybe. Sure, why not? Let's look at this next one. Ooh, new variable. I mean, it's not really any different, but we got the antiderivative or the indefinite integral of the quotient 4 plus 6t minus, I think that's a 7t squared. Hard to read. Divided by 2 times the square root of t dt. There's a couple different ways to go about this. I personally prefer the way where we think about rewriting as each thing divided by the denominator. And I should say, this is really only applicable if you have a quotient where your denominator is one term. Like if my denominator was t plus 5 or something else that had addition or subtraction, I couldn't do what I'm about to do. I mean, I could, but it wouldn't be effective, is really the thing. So I'm going to divide each thing by 2 root t. I'm going to write 4 over 2 root t. I should have written as t to the 1/2. I'm already regretting that choice, but fine, I'll fix it next one. Plus 6t over 2 times t to the 1/2 minus 7t squared over 2 times t to the 1/2. Alternatively, not my preference. Oh, don't forget the dt. You could have also written it as ink everywhere. The integral of 4 plus 6t minus 7t squared, and then still divided by 2, but multiplied by t to the negative 1/2. Right, so dividing everything by t to the 1/2, multiplying everything by t to the negative 1/2, and then still dividing by 2. I find this to be less nice. If you like that better, though, totally fine. Here, I'm going to do the division. 4 divided by 2 is 2, and 1 over t to the 1/2 becomes t to the negative 1/2. 6 divided by 2 is 3. T to the first divided by t to the 1/2, we subtract those powers and we get t to the positive 1/2. And then finally over here, 7 divided by 2 just stays as 7 divided by 2. You could write 3.5 if you wanted to. I would not choose to. And then t squared divided by t to the 1/2, we subtract those powers, and 2 minus 1/2 is 3/2. And now we're in a place where everything is a power of our variable, so we can then do the anti-differentiation. We're going to get 2 times, okay, so here's where I'm going to start doing the addition, even if the fraction's just by in my head not showing over. So negative 1/2 plus 1 is positive 1/2 divided by 1/2. 1/2 plus 1 is 3/2. And instead of dividing by 3/2, I really should just start multiplying by the reciprocal. So I should say times 2/3 instead of dividing by 3/2 to save myself some steps. Minus 7/2 times, I usually like to leave the space out in front actually. T to the 3/2 plus 1 is t to the 5/2. Instead of dividing by 5/2, we're multiplying by the reciprocal, 2/5. And of course, as always, the plus c. As always, for an indefinite integral or for an antiderivative, when we start talking about definite integrals, we will not have a plus c. I would simplify this because dividing by fractions is terrible. I'd write this as 4 times t to the 1/2 plus 3 times 2/3 is 6/3, which is 2 times t to the 3/2. 7/2 times 5/2 times 2/5. The 2's cancel and you get 7/5 t to the 5/2. Let's see. This next one's a little tricky. We can do it though. All right, I'm just gonna keep going. If you have questions or clarifications, don't wait. All right, next one is the antiderivative of secant of 2x times tangent of 2x plus e to the 3x plus 4 to the x. And yeah, this one's a little tough, I'm not gonna lie. All of these kind of have a little bit extra to them. So let me ask everybody. Let me say to everybody, there is a function whose derivative is secant of x times tangent of x. Now ignore the 2x for a second. There is a function, the derivative of some function is equal to secant of x times tangent of x. What is the function that needs to go there? It's a trig function. It's not tangent because the derivative of tangent is secant squared. It's definitely secant. The derivative of secant of x is secant of x times tangent of x, which means the antiderivative of secant of x times tangent of x is equal to secant of x. I really, really, really can't stress enough how much I want you all to be aware of this relationship. If you take the derivative of something and you get, right, whatever the derivative is, the antiderivative of that gets you back to where you started. Or in other words, the names, you say it all. The derivative and the antiderivative undo what the other one does. And yeah, with the antiderivative, you have to tack on a plus c. But they're still getting you, right? The derivative secant is secant tangent, the antiderivative secant tangent gets you back to secant. So now here's where we have to be a little bit more careful. I'm trying to find the antiderivative of secant of 2x times tangent of 2x. Or in other words, I'm asking the question, the derivative of what function is going to give me secant of 2x times tangent of 2x? Well, what seems like a likely candidate? Not secant of x, but secant of... Yeah. Now here's the deal. We're almost correct. But if I take the derivative of secant of some stuff, and the answer is secant of some stuff times tangent of some stuff, I also have to multiply by the derivative of this stuff because of the chain rule. So the problem is the derivative of secant of 2x is actually secant of 2x times tangent of 2x times 2. So how do I fix this? Well, how do I get rid of that 2? What can I multiply by to get rid of it? 1/2. But I can't just multiply one side by 1/2. I also have to multiply the other side by 1/2. So here's what I want you all to see. I want you all to look really clearly. The derivative of secant of 2x is secant of 2x times tangent of 2x times 2. The derivative of 1/2 times secant of 2x is 1/2 times secant of 2x times tangent of 2x times 2. Or in other words, it's equal to secant of 2x times tangent of 2x. So what this means for us is that the antiderivative of secant of 2x times tangent of 2x, I'm gonna write the rest of this here. The antiderivative of this first part is exactly 1/2 secant of 2x. And the way I'm going to encourage you to start thinking about this is that if when you took the derivative of something, you would end up multiplying by a constant because of the chain rule, the antiderivative is going to make you divide by that same constant. So let me ask everybody, if I took the derivative of e to the x, what would I get? What's the derivative of e to the x? Everybody say it. Thank you so much. What's the derivative of e to the 3x? Right. So since the derivative of e to the 3x made me multiply by 3, the antiderivative of 3x is going to make me divide by 3. The antiderivative of e to the 3x is going to be 1/3 e to the 3x. Because if you take the derivative of 1/3 times e to the 3x, you will get 1/3 times e to the 3x times 3. And the 1/3 and the 3 will cancel each other out. You know, just have e to the 3x. Now, the 4 to the x here part I actually kind of wanted to change because it's a little bit challenging. But we do know what the derivative of 4 to the x is. I know it's been a minute. But the derivative of 4 to the x is 4 to the x times what? Awesome. Thank you so much. So I can try. Yes. Sorry. I know. Today feels less great than usual. Is that better? Okay, good. You're always welcome to ask for me to change things. I'll try to always make it as easy to see as possible. So it's not quite because of the chain rule, but I mean, it kind of actually is. But I'm gonna say here, the derivative of 4 to the x is 4 to the x times a constant. Natural log of 4 being a constant. It's like 1.38 or something, I don't know. So if the derivative makes you multiply by a constant, the antiderivative is going to make you divide by that same constant. So the antiderivative of 4 to the x is going to be 4 to the x divided by the natural log of 4. Now, what I'm not saying here, but what we're going to say soon, is that this is really all a shortcut for some easy u substitutions. So we will talk about u substitution today in a little bit, but I'm kind of leading you to down this path of these are some u substitutions that eventually you're going to want to do this without actually having to write a u sub at all. Like when we do the integral of e to the 5x later on, you could do a u sub for sure. But I want you all to be able to do that integral without having to do a u sub because it comes up so often. You want to be able to do some of these things without having to do so much work. Let's look at these last few examples here on this handout. So here comes number 7. And these are true or false questions, or right or wrong. I like true or false better though. So true or false. The integral of 5x plus 1 cubed dx is equal to 5x plus 1 to the 4th divided by 4 plus c. And here is the typical tactic for answering a true or false question about an integral. You don't try to find the integral or antiderivative of this. You try to find the derivative of the thing you think it's equal to. So let's check. We're going to take the derivative of, I would probably choose to rewrite this as instead of 5x plus 1 to the 4th over 4, I would write it as 1/4 times 5x plus 1 to the 4th plus c. If we take the derivative of that, the 1/4 hangs out. The derivative of some stuff to the 4th power is 4 times my stuff to the 3rd power times anybody? The derivative of the stuff plus the derivative of c, which is 0. Is that what I started with? No, I'm off by a factor of 5. This is equal to 5x plus 1 cubed times 5, which is not 5x plus 1 cubed. So since the derivative of this is not that, the antiderivative of this is not that. We have to have that two-way relationship. Cool. So if anyone ever asks you, is this integral equal to this thing? Don't try to figure out the integral. Try to take the derivative of the thing, because that's usually the easier process. And it's also what they want you to do. Like that is, whenever someone asks you a question like that, that is what they almost always mean for you to do, is don't try to actually anti-differentiate this. Try finding the derivative. Like in this next question, we don't even have the tools yet to find the antiderivative of 3x squared times sine of x, which would require integration by parts, which we have not learned yet, which we will learn, but we're not there yet. But true, false. Oh, sorry, I should have circled that this is false up here. False, definitely. This is equal to x cubed times negative cosine x plus c. And if we'd forgotten how the product rule works, then sure, this would be true. But it's not, because we know how the product rule works. If we check the derivative of x cubed times negative cosine of x plus c, we have to actually use the product rule. Derivative of x cubed is 3x squared times the other piece left alone, plus, now we do it the other way, leave the x cubed alone, and the derivative of negative cosine is negative sine, just sine. And then the derivative of c is 0. I don't think you really need to write the plus 0, but okay. And that is definitely not the same as 3x squared times sine of x. So also false. That integral is not equal to x cubed times negative cosine. Or in other words, if you're integrating a product of two things, you cannot just take the antiderivatives of each part and multiply it together. Disappointing, I know. But the integral of 3x squared times sine of x is not equal to the integral of 3x squared times the integral of sine x. We will develop a way of finding it though. Do I have enough room here? No, I should be good and not trying to squeeze things into the bottom segment of a piece of paper here. Last one on this little handout here, number 9. The integral of x, again, true, false. The integral of x cosine of x dx is equal to x times sine of x plus cosine of x plus c. And obviously it must be true because the other two were false. Is how I would feel about this if I was taking this. If I was like, well, sure, the first two were false, this one's probably going to be true. That doesn't mean we can't not check it, but it's often how people think. So let's do the same thing. We're going to check by taking the derivative of right-hand side. So the derivative of x times sine x plus cosine of x plus c. So for x times sine of x, we also have to use the product rule. So we're going to get the derivative of x is 1, leave the sine alone, plus, leave the x alone, the derivative of sine of x is cosine of x. And then the derivative of cosine of x is negative sine of x, plus the derivative of c is 0. And then let's see, sine of x minus sine of x, those add to 0. So I'm left with x times cosine of x, which is what we started with over in the integral. So that works out. That derivative is equal to x cosine x, which means it is true that the antiderivative of x times cosine of x is equal to x times sine of x plus cosine of x plus c. And we will learn how to do this eventually when we learn about the integration by parts method. But this is definitely an integral that requires integration by parts. Cool. Cool. Let's see. Let me look something here. Anything I'm sure it's that. So yeah, we'll say that. Cool. Oh, initial value problems. That was the other thing I wanted. Give me 1 sec. Sorry, I just want to see one thing. Okay, sorry, I had notes. I always have notes somewhere that are hiding from me. Oh yeah, we want to do all that too. Okay. What time is it? Yeah, we got time. We got a lot of time. Okay, let's see. Let's do that first. We do that. I want to have a handout too. I have so many things. Sorry. So a few things just to have in your kind of arsenal of tools. You definitely need to know your trig derivatives. So I want to point out that we supposedly know all the trig derivatives. Derivative of, I want to write this in a less terrible way than we usually do. Nope. So Derivative of sine equals cosine. Derivative of cosine equals negative sine. So we also know the antiderivatives. The antiderivative of cosine is equal to sine plus c. The antiderivative of sine is equal to negative cosine of x plus c. The derivative of tangent of x is equal to secant squared of x. The derivative of cotangent of x is equal to negative cosecant squared of x. For antiderivatives, we're just reversing the order, right? The derivative of tangent is secant squared. The antiderivative of secant squared is tangent. So your instructors expect that you know all these already because you know these derivatives. So you already know these antiderivatives once you understand the relationship. And then we don't like to take the antiderivative of the negative thing. We like to move the negative to the other side. So instead of saying the antiderivative of negative cosecant squared is positive cotangent, we like to say that the antiderivative of cosecant squared is negative cotangent. Antiderivative of cosecant squared of x dx is negative cotangent of x plus c. I like parentheses. Finally, the last two, the derivative of secant of x is secant of x times tangent of x. And the derivative of cosecant of x is negative cosecant of x times cotangent of x. Then we have the antiderivatives. The antiderivative of secant of x times tangent of x dx is equal to secant of x plus c. And the antiderivative of positive cosecant of x times cotangent of x dx is negative cosecant of x. So these are all the ones we should know right off the bat because we already know the derivatives of all these things are all these things. So we know the antiderivatives of all these things are these things. We will also learn about the antiderivative of tangent and cotangent, but that's not right this moment. Yeah. Sure. Let's look at an initial value problem or two, and then we'll start talking about U sub after that. So initial value problem. So find the function f of x given that the derivative is equal to 6x squared plus 8x minus 2. And we know that f of 0 is equal to 9. The words we're not saying, even though we mean them, are find the antiderivative and then figure out what the constant c is using this initial condition. So whenever someone gives you, like says find the function and gives you what the f of something equals something, it doesn't have to be f of 0, it could be f of 13 equals 2 or whatever value they decide to give you. That just means your job also includes solving for the constant c. So first, of course, yes, yeah. You're welcome. So first, we're going to find the antiderivative of f prime. In other words, f of x. You can use whatever notation you like. I'm going to write it as the antiderivative of 6x squared plus 8x minus 2. That's going to be 6x cubed over 3 plus 8x squared over 2 minus 2x plus c. And that is equal to my f of x. I would probably simplify a little bit before I plugged in my point. So I would say f of x is equal to 6/3 is 2x cubed. 8/2 is 4x squared minus 2x plus c. And then I'm going to plug in. And I made it kind of easy here. Plug in x equals 0 and f of 0 equals 9 to get 9 equal to 2 times 0 cubed plus 4 times 0 squared minus 2 times 0 plus c, or in other words, c equals 9. It is a mistake to stop here because the thing they asked us to find was the function. Yeah, we found the function with a c in there and we found the c value, but we really should take the time to write out that our final answer is that f of x is equal to 2x cubed plus 4x squared minus 2x plus 9. That's how we should actually finish this off. Yeah, let's look at that one. Sometimes initial value problems come up in kind of a kinematics or a physics connotation. Right. Let's look at this example. A rocket takes off with a constant acceleration of 20 meters per second or meters per second squared. How fast is it going? And how high is the rocket after 3 seconds? Okay. So a lot of what this problem is going to require of us is some common sense about what we have happening at the beginning. So the rocket takes off from the Earth. And at the moment of liftoff, what is its height? Well, technically it's still on the ground, so its height is 0. Similarly, at the moment of liftoff, its speed is 0. It's not technically moving yet. So our initial velocity is 0, our initial height is 0. We're going to use that as we go on. So they're asking us, how fast is it going? In other words, what is the velocity at time equal to 3 seconds? And what is the height or position at time equal to 3 seconds? Thanks. So we have to know or be told that velocity is the derivative of position, and acceleration, or the rate of change of velocity, is the derivative of velocity. So we're really just talking about rates of change here, right? Velocity is how your position changes. So the derivative of position is velocity. Acceleration is how velocity changes. So the derivative of velocity is acceleration. And working backwards, if acceleration is equal to the derivative of velocity, then the antiderivative of acceleration is equal to velocity. Usual relationship. If the derivative of something is equal to something else, then the antiderivative of that derivative is of the something else is equal to the original function. So we were told that the acceleration was 20 meters per second squared, meaning it's constant, right? Every second, our speed is increasing by 20 meters per second. So time equals 0, our speed's 0. And after 1 second, our speed should be 20 meters per second. After another second, our speed should be 40 meters per second. After another second, our speed should be 60 meters. Actually, we can answer the question, at least that part, without even doing the integral, really. We're still going to do the integral. So the antiderivative of 20 is going to be, notice I'm using t instead of x. T is pretty common when you're talking about time. It's going to be 20t plus c. That's going to be my velocity at time t. And now we should use the initial condition that we know that nobody wrote down to figure out what c is. So we know that the velocity at time 0 is 0 meters per second. Right? And when it's taking off, it doesn't actually have any speed yet. So we can say that since we know that v of t is equal to 20 times t plus c, if I plug in 0 for t, you get 20 times 0 plus c, and that's equal to 0. Well, that means c has to be 0. So really, our velocity at time t is just 20t. Which means, like we kind of just implied it was going to be, we want to find the velocity after 3 seconds. Well, the velocity after 3 seconds is going to be 20 times 3, which is 60. 60 watts. What are my units here? Well, acceleration was being measured in meters per second, so velocity should be measured in meters per second. Whenever you, it's kind of weird. Whenever you anti-differentiate and you're thinking about units, you kind of multiply by that unit. So meters per second squared is length per time times time. And then if we multiply by a time, now we're getting just length per time. Meters per second squared, multiply by a second, you get meters per second. Multiply by another second, and you just get meters or position, which makes sense. So every time you anti-differentiate, you kind of up your dimensionality. It's not exactly precise, but it's true. So let's talk about position. So just like acceleration is the derivative of velocity, velocity is the derivative of position. So I'm always trying to squeeze things in. Let's just use more paper. So velocity is the derivative of position. And also, acceleration is the derivative of velocity, is the second derivative of position. Not that you actually need to have that here, but it is true. And if you want, you don't have to take the third, you know what the derivative of acceleration is? It's called jerk. So think about you like you're driving your car and then you slam on the gas to jerk forward to get past someone. You literally like you change your acceleration. You're accelerating and then you accelerate faster. You jerk forward. It is actually called jerk. Or you can think of slamming on the brakes, right? If you slam on the brakes, you decelerate at a faster rate, you jerk back. And not back, but like, right, you kind of so that's what the third derivative is called. It's kind of neat. Not important at all. Anyway, to find the position h of t, well, we're going to have to anti-differentiate both sides. The antiderivative velocity is the position or the height. So I'm going to integrate 20t, or anti-differentiate, and I'm going to get 20t squared over 2 plus, I would normally use a different concept, but since I already figured out what the previous c was, I'm just going to use c again. Now, we also know that the position at time 0 is also 0, right? When this thing is blasting off from the ground, its height is 0. So we can then use that to find c and say, that's h of t. So simplifying, h of t, 20 divided by 2 is 10t squared plus c. And then we know that h of 0 is 10 times 0 squared plus c, but it has to be 0. So not surprisingly, we also get c equals 0 again. So our height equation is just 10t squared. And if we plug in t equals 3, we get h of 3 equal to 10 times 3 squared, which is going to be 90. 90 meters, right? Because we're talking about how high it is, and we're measuring things in meters per second or meters per second squared. So the height should just be measured in meters.
How strict are going to be on units?
No idea. I mean, I would. So the nice thing about units is, if you think about what you're trying to describe, as long as you like, it could be, right? My height could be measured in meters or feet or miles or whatever length it is. My velocity is always going to be in unit of distance divided by unit of time, whether that's meters per second or feet per second or miles per hour or I don't know, light years per, I don't know, like, right? It's always a distance divided by a time. And then acceleration is always a distance divided by a time squared. So meters per second squared, feet per second squared, miles per hour squared. Seems like a weird thing to say, but it would still measure an acceleration, or miles per hour per second. But I don't know how strict they will be. Usually people are not super strict about it, but it can vary. So there's another example of an initial condition type of question where you have to know the initial conditions to actually find the function fully so you can answer the question. Let's talk about U substitution, which, in my opinion, will probably come to be your favorite method of integration. It's kind of like, if I'm ever trying to anti-differentiate something and I don't know what to do, U substitution is always what I try to do first. Let's look at an example. Let's say we want to find the antiderivative of, let me think about this for a second here. Sure. Yeah. Sorry, oh yeah, now I'm thinking. Let's say we have, sure, 5x squared plus 1 to the third times 10x dx. Yeah, that'll work. And we're going to do this two different ways. We're actually going to multiply it out first. So I want you to see that it really does work. So you guys remember how to multiply out something cubed? Remember what a plus b cubed is? You guys know Pascal's triangle? Have you heard of Pascal's triangle? It's kind of neat. So real quick, you don't have to write this down, but 1, 1, 1, and then you get the middle terms by adding like 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 1 is 3, and so on. 1, 4, 6, 4, 1, and so on, and so on, and so on, forever and ever and ever and ever and ever. But the cool thing about Pascal, there's lots of cool things about Pascal's triangle. One of the cool things is that every row gives you the coefficients of the binomial expansion. Meaning 1 is the coefficient of a plus b to the 0th power, which is 1. And 1 and 1 are the coefficients of a plus b to the first, which is just 1a plus 1b. And 1, 2, 1 are the coefficients, I'm gonna write down here, of a plus b squared. That's 1a squared plus 2ab plus b squared. Or a squared plus 2ab plus b squared. And 1, 3, 3, 1 are the coefficients of a plus b cubed. It's 1 times a cubed plus 3 times a squared times b plus 3 times a times b squared plus 1 times b cubed. And it goes on and on and on and on and on. If I said what's a plus b to the fourth, it would be 1 times a to the fourth plus 4 times a cubed b plus 6 times a squared b squared plus 4 times ab cubed plus 1 times b to the fourth. And the pattern is that these are all the coefficients, and then you start with a to the highest power, and then the power of a becomes 1 less every term, and the power of b becomes 1 more every term. That's kind of it. So using that, we can say that 5x squared plus 1 to the third is going to be, well, so this is like my a, and this is like my b. So it's going to be a cubed, so it's going to be 5x squared cubed plus 3 times a squared times b plus 3 times a times b squared plus b cubed, all that times 10x. Okay, it's gonna be a little bit of work here, but we'll get there. So 5 cubed, anybody? 5 cubed? Not 75, it's 125. I got 125, and x squared cubed is x to the 6th. 5 squared is 25, and 25 times 3 is 75. And x squared is x to the 4th. 5x squared times 3 is going to be 15x squared plus 1. I feel like I've got a little weird here. Finally, all that times 10x. Okay, so let's distribute the 10x, and we're going to get 1,250 x to the 7th plus 750 x to the 5th plus 150 x cubed plus 10x. Yeah, I might have picked an example. It's a little too gross, but we will get there, I promise. So, anti-differentiating now, we're gonna get 1,250 x to the 8th over 8 plus 750 x to the 6th over 6 plus 150 x to the 4th over 4 plus 10x squared over 2 plus c. And I'm a little worried my example is a little too gross, but it's going to be okay. That seems terrible. Also, if that power were 30 instead of 3, it wouldn't be actually impossible, but it might as well be. Multiplying out something x squared plus 1 to the 30th power is too much work. Yeah, that's exactly where we're going, Tiffany. We're exactly going to do a U sub instead. The point is I want you to see that when we do the U sub, we will get almost the same answer. The same enough. So let's look at the U sub and see what happens. So here's the idea with the U sub. When you have an integral of something like this, it would be really, really, really convenient if something that was in there, its derivative was also in there. And here, that's exactly going to happen. If I choose u to be equal to 5x squared plus 1, and the way I'm thinking about choosing u is twofold. I'm trying to choose something for u. If I take its derivative, I also have that in my integral, and that is certainly true here. The derivative of u with respect to x is exactly 10x, and I have a 10x in my integral. The other thing that I usually look for when I'm thinking about what might be a good candidate for u is something that is stuck inside some other function. It's like the insides of a sine or a cosine or a being raised to a power or a square root. So here, oh, this 5x plus 1 is being raised to the third power. It's like I have some stuff to the third power, and I'm looking for u to be my stuff. So then this is going to be a translation problem, meaning I have to translate this integral from the language of x completely to the language of u. You cannot have x's and u's together at the, like in the middle you can, that's fine, although I don't usually like to. But at the end of the day, it should be all x's or all u's, not some of each. There's probably like 3 different ways people like to do this. I will show you what I prefer, but then we can talk about what your teacher is doing. I prefer to say, oh, look, I have a 10x times dx. So I'm going to rewrite this so that du is equal to 10x times dx. I personally do not prefer to isolate dx, even though some people do. So I would like to say, oh, look, this is equal to du. I also want to stress it is almost always in your best interest to make sure you take care of dx changing into du before anything else, because that has to happen. Now, I can observe that this part here, that's equal to u. So I can rewrite my integral as the integral of u to the third power du. And I know how to integrate u to the third, or x to the third, or t to the third. It's going to be u to the fourth divided by 4. Plus c. Now, if you're doing an indefinite integral, aka an antiderivative, you always have to start, sorry, you always have to end with the same variable you started with. This question says, what function has a derivative that's equal to this? It's not u to the fourth over 4, it's a function of x. So we have to change back to the variable we started with if it's indefinite. For definite integrals, we'll talk about later on, you can switch back or not, depending on how you want to deal with things, but you don't always have to switch back to what you started with. But for indefinite integrals, aka antiderivatives, we always have to switch back. So we're going to rewrite this as 5x squared plus 1 to the 4th over 4 plus c. And now I would probably recommend not writing out the rest of what I'm about to write here, because I do want to do the terrible amount of work it's going to take to actually see that these are the same. So if we multiply this out using, again, Pascal's triangle, and again, I'm going to recommend maybe just watching and not writing this all down. I'm going to get my thing to the 4th, so 5x squared to the 4th plus 4 times 5x squared cubed times 1 plus 6 times 5x squared squared times 1 squared plus 4 times 5x squared to the 1st times 1 cubed plus 1 to the 4th. I'm just using that Pascal's triangle again, but now it's the 4th pattern, the 1, 4, 6, 4, 1 pattern. So let's, okay, multiplying it out. Ugh, shoosh, oh, boys. So what's 5 to the 4th? It's 625. X squared to the 4th is x to the 8th, or 4, plus 4 times 5 cubed is 125. X to the 6th over 4. I'm breaking it up just because I want to break it up. It's because I'm trying to make sure, I'm hoping to make sure that it looks the same as this up here. And then I'm going to have 6 times 25 is 150, x to the 4th over 4, plus 4 times 5x squared over 4, plus 1/4 plus c. So now let me ask you, are these the same? So is 1,250 over 8 the same as 625 over 4? Definitely yes. You can multiply this fraction by what over what to get that fraction. 2 over 2. 625 times 2 is 1250. 4 times 2 is 8. Is this the same as that? Ugh, maybe. Let's cancel the 4s. Oh, is that the same? Yeah, it is. Cancel the 4s there, you get 125. And 750 divided by 6 is also 125. 750 divided by 3 is 250. 250 divided by 2 is 125. So cool, that works out as well. 150 divided by 4 is 150 divided by 4. 10 divided by 2 is 5. That's 5. Uh-oh. Oh no. Oh no. Oh no. Not oh no. Constants are fine. If you're antiderivative and you're antiderivative and you're antiderivative, if you're all off by a constant, you have 1/4, I have 1/8, you have whatever, that's okay. Because the derivative of this and the derivative of this, well, the derivative of this part is the same as the derivative of this part, and the derivative of this constant, which is 0, is the same as the derivative of this constant, which is also 0. So it's really okay to be off by a constant. So I have to stress these are the same. So instead of doing all of this work of multiplying this out and then taking the antiderivative, what we're instead going to do is we're going to do this process of u substitution. And we're not going to do all this dumb stuff I did here. We're going to leave our answer like that. The only reason we did this was just to see that they were actually the same. But we don't have to do that in the future. So, big picture u substitution, you're trying to look for an inside piece whose derivative is also inside the integral. Let's look at some more examples. Yeah. Yes, these are so these are still instructions. These are just telling us to anti-differentiate, but now they're telling us to anti-differentiate for u instead of for x, which is good because we have u's, not x's. Yeah, great question. Thank you. So let's look at something like, how much time we got? We got time. Okay. Let's look at something like the antiderivative of cosine of x cubed times, sure, we'll make it easy. No, we won't. X squared dx. Most people would probably write this as the integral of x squared times cosine of x cubed. It is more normal to write the x squared in front of the cosine of whatever. So based on the two things we just said about how we might want to pick a choice for a u substitution, What might be a good choice for you here? Right, the thing that's stuck inside the cosine function. Now let me ask you all, is the derivative of x cubed also in our integral? And whatever answer you say is going to be right. You can say no, you can say yes, and you're both right. No, it's not exactly there. Because you're right, the derivative of x cubed is 3x squared. The better question I should have asked is it close enough? And the answer is a resounding yes, because we can always adjust for a constant multiple. So you really don't care about the 3 there. I just care, is the derivative of my u something that looks close enough to x squared? Yeah, it is. We can fix a 3. So here's what I'm going to do. I'm going to write my integral like this, and then I'm going to try and make this look like an x squared times a dx. So I'm going to do it this way. Most people skip this step and go straight to writing du equals 3x squared times dx. That's totally fine. I'm going to do the thing, and I'll show you both ways for this one because I think it's a good example. Here's what I would do, and then we'll do it a different way. I would do this. Here's the James way. The James way is to try to make the right side of this look like something you have. So I'm going to divide both sides by 3 or multiply both sides by 1/3. Say 1/3 du is equal to x squared times dx. Great. So now the x squared times dx inside my integral, I'm always taking care of the dx first. That's going to be equal to 1/3 du. Literally, it's on the page. X squared times dx is equal to 1/3 du. And then cosine of x cubed, well, the x cubed gets to be replaced by u. That was our choice for u. So now we get to rewrite the integral. We're going to write it as the integral of cosine of u times 1/3 du. Normally, I would not even write that 1/3 in there. 1/3, well, it's not that I wouldn't write it at all. I would write it out in front of the integral. Because any constant multiple, just like with a derivative, you can bring it out in front. With an antiderivative, you can bring it out in front. So I want you to get in the habit of whenever you have a constant like 1/3 or 1/2 or 4 multiplied by everything else in the integrand, just bring it out in front. Write it as 1/3 times the antiderivative of cosine of u. Okay, we're ready to do what the instructions told us to do. The instructions are telling us to find the antiderivative of cosine of u. What is the antiderivative of cosine of u? Is it positive sign or is it negative sign? Positive sign. So you get 1/3 times sine of u plus c, right? We still need the plus c. And then finally, since it's an indefinite integral, an antiderivative, we have to go back to the variable we started with and write it as 1/3 times sine of x cubed plus c. You should notice that if you took the derivative of this, the derivative of 1/3 times sine of x cubed would be 1/3 times cosine of your stuff times the derivative of your stuff. So a quick note here. The derivative of 1/3 sine of x cubed is equal to 1/3 times cosine of your stuff times the derivative of your stuff. And not surprisingly at all, 3 and the 1/3 divide to 1 or multiply to 1, whatever you want to say, and you get x squared times cosine of x cubed, exactly as we should. So once again, we're seeing the derivative and the antiderivative just undo what the other one does. The antiderivative of cosine of x cubed times x squared is 1/3 sine of x cubed, and the derivative of 1/3 sine of x cubed is cosine of x cubed times x squared. Always, always, always going to work that way. Now, maybe you don't love the way I've done this. That's fine. You do not have to do it exactly the same way I do it. Something that people often prefer to do instead is the following. And yeah, I think we have enough room to put it on here. I kind of would like to put it on the same page. So you could also do it the following way. Still with the same u sub. But then when people pick u equal to 3x squared and get du equal to, sorry, I do sure. du equal to 3x squared dx. Sorry about that. And we picked x equal to u to, oh my God. What did we pick? What was our choice for here? Please tell me, I've forgotten. U equals what? Thank you. So we picked u equal to x cubed. We got du equal to 3x squared dx. And then some people prefer to actually just isolate dx here. So they like to say, okay, du divided by 3x squared equals dx. I don't love this, but that doesn't mean it's wrong or not okay. It's just not the way I like to do it. It's a perfectly valid way of doing it. So then we're going to take our integral and we're going to rewrite it. And this is where things get a little bit funky. We're going to say we have cosine of x cubed times x squared times dx. It is times dx, right? We don't usually say that. We just say the integral of cosine of x cubed times x squared dx, but there is a times implied there. And we're going to actually write it with x's and u's for a minute. So we're just going to replace the dx. We have cosine of x cubed times x squared times the thing that dx is equal to, which is du over 3x squared. And then immediately what you should try to do is cancel the x squared or whatever is underneath your du. And it does. The x squared here cancels with the x squared there. And then you can continue on replacing every other instance of x with whatever it's equal to in terms of u. So this x cubed here gets to be replaced by u, which is going to be the integral of cosine of x cubed times du times 1/3, which is the problem right now because I have x's and u's mixed together. I don't want x's and u's. I want either all x's or either all u's. I want all u's specifically here because I'm trying to get to u. So then I replace my x cubed with u and I get 1/3 integral of cosine of u du, which still gets us to the same place we got to over here, just in a slightly different way, which means if we anti-differentiate and plug back in, we'll get the same answer. Either way is fine. You should kind of decide for yourself what you like to do. Well, I should ask also, how did your teacher present it in class? Did he do it this way where you kind of try to make the right side look like what you want, or did he solve for dx like this? Or do you not remember? That's all fine. Like, you did one of those things. Okay. Yeah, okay. So I have what, like 5 minutes? Yeah. So here's what I actually really want you to know. I mean, okay, that's a broad statement. There's a lot of things I'd love to do. The thing I want you to take away from this is the idea of what myself and probably every other specialist at the AATC refers to as a mini U substitution, which is the thing I was talking about kind of earlier. If I wanted to find, for example, the antiderivative of e to the 6x dx. Yes, we could do a U sub. We could let u equal the thing that's stuck. I think of that as being what's inside the exponent. My u would be 6x. My derivative, the derivative of 6x is just 6. Or in the step we usually skip, we would just get to saying that du equals 6 dx. Or dividing both sides by 6, 1/6 du is equal to dx. And then I would rewrite this. I would rewrite this as the integral of, well, again, I'm always changing dx first, even though I could probably be okay with not doing that first. I'm still going to make sure that dx becomes 1/6 du. And the e to the 6x is going to be e to the u. I would pull out the 1/6, even though I don't really feel like you have to here, and do it as 1/6 the integral of e to the u du. What's the antiderivative of e to the u? Easiest one out there. It's e to the u. So we plug back in, and we get 1/6 e to the 6x plus c. Or, stated in an entirely different way, since the derivative of e to the 6x would make you multiply by the constant 6, the antiderivative of e to the 6x is going to make you divide by the constant 6. Let me show you another example. How about the antiderivative of cosine of 6x? Okay, question that's not that. What's the antiderivative of cosine of x? Right. So the antiderivative of cosine of x is sine of x. The antiderivative of cosine of a multiple of x is going to be sine of that same multiple of x. But what do I have to do to adjust? Divide or multiply? Right. Divide by 6. Or you could say, I guess you could say multiply by 1/6. I'm always thinking of it as division. Right? Because again, if I take the derivative here, the derivative is going to end up multiplying by that 6 to cancel out the 1/6 there. So I need that 1/6 to account for that eventual chain. Because, by the way, in case you didn't know this already, and it's okay, you shouldn't necessarily know this already, but just so you all know, this U substitution process, you're really just undoing the chain rule. You're finding the inside piece, and then that inside piece is your stuff. And we always end up multiplying by the derivative of the stuff. Well, look, right, when I here, no, that's the, yeah. Like when we did the other example, right, when we did this, like the integral of, I don't know, let's make something up. Sure, he says, when he can't think of anything. If we did something like the square root of x cubed plus 1 times 3x squared dx, that x cubed plus 1 is your stuff. And this 3x squared is your stuff prime. So you're always looking for the stuff in the chain rule whose derivative is also there, or something that's close enough to its derivative, right? The 3 there is inconsequential. We don't really, this 3 there, you don't really have to have that for things to still work out. Sorry, I'm just trying to, okay. So continuing this sort of vein here for one more second, if I said, what's the antiderivative of, say, secant of 6x times tangent of 6x dx, well, we know the antiderivative of secant of x times tangent of x is just secant of x. So multiplying x by a constant means that we have to divide our antiderivative by that constant. So our answer here should also be 1/6 times secant of 6x. Yes, all of these you could do with a u sub. In each of these, you could have let u equal 6x and then gotten dx equal to, oh, look, 1/6 du, which means you end up dividing by that 6 or multiplying by 1/6. So I want you to be able to do this with relative ease and speed, so you're not having to actually do a u sub every time you're trying to do one of these small ones here.